Good afternoon. My name is Evan Luco. I'm the lead of our this year's automation storage and retrieval system capstone group. Today you'll hear from Nadine, Hans, Carl, and myself in regards to our progress on SAIT's ASRS system. We'd like to thank our customer, Chris Dick, our technical advisor, Dan Barrett, and our communications advisor, Joan Magnuson, as well as everyone in attendance today.
Hello everyone, my name is Nadine Abuforn and I am responsible to keep the time management for this group, and I will go over our constraints.
And I'm Carl and I'll be going over the competitor research.
My name is Hans McDonald and I'm here to explain the state of the control cabinet and the control box.
Thanks. So today for our agenda, we'll be going over our project problem statement, our problem analysis, our project scope, the constraints and limitations, where we started with the project, some ideas that we've had for additions to the control box. Then we'll be going over our competitors' research, looking into what we have on our counterweight system, what we've come up for design concepts for moving forward, the conclusion to our presentation, and then we'll finish out with our Q&A session. So in order for the MET Mechatronics Factory to become a reality for future students at SAIT, the ASRS system has to be fully repaired. There are motors on it that have to be calibrated. A human machine interface has to be applied to elsewhere in the lab. We need to have communication between them and the IRB 140s and Robotino equipment in the lab. And we have to complete documentation for future maintenance and use for our system. Due to the limited space in the robot work cell, the lab doesn't allow for easy storage of numerous items. So an ASRS would allow that to be filled. Also, due to the hazardous nature of the speed and the weight of the IRB 140, we can't obviously have humans in there giving items within the work cell. So that allows that as well. In addition, humans aren't required to search for any of those kind of items that are needed for processing. The system itself can just go and retrieve it from where it's already been programmed to, or where it knows that it's stored. We broke our project down into 5 major objectives that we could begin working on immediately. Due to the progress from previous years' groups, we were met with many constraints moving forward for our direction.
So some of our constraints that are affecting us negatively, given the current global situation, we're limited by lab time and we can't go outside of designated hours. We're also restricted due to safety, so no one is allowed to be in the work cell while somebody or another person is programming the IRB 140. As you can see here on the bottom right, the IRB 140 has a sharp end effector, and that can be very hazardous, let alone the weight of or how powerful the IRB 140 is. Another thing is limited budget, as we want to reduce the cost of our required materials and utilize available resources, whether it's from home or in the lab lying around, and limited documentations from previous years. So files received from previous years are either outdated or barely relevant to us, and we had to alter them to fit our criteria, as you will see in the schematics later on in this presentation. Another thing is motor and conveyor speed. So they're set to default, and that limits our production. And finally, we are limited by the width of the conveyor belt. We can't design a tray outside of the dimensions, and we have to keep them in our parameters.
When the team started the project, the last group left the control cabinet and control box in this state. So in order to organize and put everything in order, me and Nadine decided to handle the cable management. We also received the schematics of the last group by our client, and most of them are unreadable. I am in charge of transcribing the schematics and redrew them as neatly as possible. Looking at the control cabinet, what we discovered is that some of the cables are not connected and some are not labeled, as it should be. It is also difficult to know which cables goes through to the control box, so we decided to use a multimeter to determine if there is a relationship between cables on both sides, and label them as necessary. Since we received the schematics for the control cabinet, we can start the cable management and organize the cables. For the non-connected cables, we discovered that there are cables that control the z-axis of the ASRS. We will be looking to fix that as well. Now for the now for the control box, as you can see that the control box is quite messy and the terminal block is not bolted onto the control box. We are looking to fix that and bolt them properly. We are also working on where to place the control box so it is not just sitting there. For the meantime, we will think about it after we deal with the connections between the control box, sensor, and the control cabinet. In this slide, this is the schematics for the control box. On the picture on the left, the drawing did not say anything about the z-axis connection for the ASRS. So we proposed a new schematics, which is on the right, and decided to separate the three axes and put them in different terminal blocks. This will make things much more organized and easy to maintain. If by some chance the ASRS stops working, the e-stop connection is good as is, and we did not touch it any further.
In order to find possible areas of improvement for our current ASRS system, we looked into other ASRS systems that are being implemented by other companies to see if we could emulate some of their elements into our system. The first system we researched, which can be seen on the left, is called the Unit Load ASRS Compact System, which reduces placement and shipment time, and it has its inventory continuously monitored. However, it requires a bigger space than the actual work cell itself, which would be problematic implementing here at SAFE. The picture on the right shows the flow robot system that is used by Amazon in their warehouses, which utilizes robots on the factory floor that operate with optical sensors to move shelves to retrieve and store the required items the operator selects. This fully automated system is incredibly safe since the robots do all of the heavy lifting away from factory workers. However, this system is not normally used for high velocity settings like the one at our lab. The third concept that we researched into was the system that can be seen in the left picture, which is called the vertical lift module. This system is designed to customize and fit inventory changes in order to suit the operator's needs. It's already equipped with automatic tray extractors that dispense trays at the operator's waist height, which makes pickup a lot more easier physically. On top of that, it is also extremely compact, saving up to 85% of space. The system in the middle is the vertical carousel system, which rotates shelves to bring the required item to the operator. This system does a great job of eliminating the need for robot pickups, as well as allowing for the simultaneous pickup of multiple items. However, it's only effective in low to medium velocity factory settings. The last system on the right, which is called the vertical buffer module, uses a built-in conveyor belt system which dispenses items in its inventory for pickup. This system would be very useful to emulate because it is very cost-effective, useful for small applications, and it has the ability to dispense multiple items thanks to its conveyor belt system.
All right, thanks, Carl. Using these designs, when we went forward and looked at our counterweight system, the previous group last year had used a PVC pipe to center the counterweight system, and it just used zip ties to connect it all. It was functional, but it's extremely inaccessible and clearly, obviously, not the long-term solution for the whole system. In addition, we went and laid out how we understood our ASRS system is going to, how we plan for it to function. That way we could establish constraints for going forward for these systems. With the input of our customer and technical advisor, we laid out demands and wishes for the counterweight and tray subsystems. And that allowed us to construct our morphological chart, which displays our potential different ideas for moving forward, both the with the counterweight, the effector, and the tray systems that we have. You can say here, since our technical advisor said that we aren't allowed to cut the actual trays, we made suggestions for potentially having a second tray on top of it, using other trays that are available in lab to potentially mount on top. In regards to our effector on the system, we have potentially using that PVC pipe again in kind of a bulkhead, or sorry, a more kind of panel system that could be attached and deattached to actually access the place where all the counterweights are stored, or potentially using some other means like with keeping tension on both cylinders to actually keep the place for the weights to be stored centered. We also have to update the means that the counterweight system actually attaches to our effector, because the bracket that's attached to it is bending and coming off. So we had the idea suggested about using a metal end cap with a bracket to have the counterweight system easily accessible. We also had some other ideas about using a band or some potential carabiners in addition along with those systems. Now that we've caught up to the present, we can conclude, and you can see the limitations presented in our project and how those limited our design choices. Where we began with the project in the dire state that the system's in. With our new ideas based on our research from industry, we plan to eliminate many of those issues that we were presented with at the beginning and allow ease of use for both the students for maintenance and normal use for the system in the future. Thank you for your time and attention. Now, if there are any questions, we'd be more than pleased to answer them at this time.
I have a few comments more so than questions. This is the third year that I've been a part of either participating in or being in capstone projects. So I've seen 3 different iterations of this ASRS project. And I feel like a broken record when I have to say, you probably shouldn't be laying a bunch of blame on the group before you. Yes, it may have been a mess. Yes, it may not be the state you want it to be, but from a professional standpoint, it doesn't really come across well when you start talking poorly about previous projects. That's really my only comment on that. I think you guys have a great scope on what you're doing. It's just, like I said, you guys can say that on your own time, but in an actual presentation with industry, may not be best to be saying, hey, these guys left us a disarray and have left us all this work that now we have to fix.
Okay, that's entirely fair.
Comment, sorry.
We only made mention of it just because it did eat up quite a lot of our time trying to get a actual proper course for the project.
I do understand that. Like I said, it's been the same problem the past 2 years as well.
Okay. We only thought mentioning of it just because it like we have to account for that time, obviously. So
yeah, I would say maybe find a different way to say, you know, the project was left unfinished, maybe, but showing images of the fact that it was an absolute mess may not be the best way to go, especially if you're trying to show like industry members, you're trying to explain your project with being, oh, we're essentially like the fix-it guys. We're not going to get anything done because we're too busy building off of what someone else did or fixing what everyone else in the previous years have done.
Okay, for sure.
Just to add on to that, very good comments from Lane. One of the things that you could do that is to a bonus and something that could help you is being able to show the previous, the state of the panel previously, and then show the success that you've actually achieved. That goes a long way, improving and showing how professional and as well as how you actually, you know, do better than the previous teams without emphasizing on being how bad it was before and more on how you guys have successfully achieved something.
For sure. We'll take that into account in the future. Thank you. All right. Were there any other questions from anyone else? Or
I also just wanted to comment that maybe I missed the part on how your unit is better than the shelf markets units. I understand there were different options that were there. The vertical carousel, I didn't understand why that wasn't too much of a difference, but I want to know more about why yours is a better pick.
In regards to that unit selection, that whole system was put in place before we got the project. So obviously, you know, we can't go and cost a new one. That's to make this one an effective use in lab. So we can't really go and change to a carousel system or any of that. That and the actual frame that we have the ASRS in lab there wouldn't really allow for that kind of system to be in place, because the shelves in each of it are actually metal bars that are holding all the trays in the system up. So it would require cutting out a lot of that stuff and implementing that if that were the case.
Understood.
So, all right. Is that all the questions then? Or comments? All right. Then in that case, thank you again for everyone for attending and for your attention during our presentation. And I'll hand it back over to Chris then.